Okay, so good evening, everyone. So today we are here to have a discussion on the week 8 session of NMR spectroscopy for biologists and chemists. The lectures that you attended in this week, we'll be trying to solve a few questions based on those concepts, and we will be also solving some numericals and some doubts that you might be having to clear your concepts and the doubts. So I'll wait for another 2 minutes so that everyone else who are there can join. So I'm Akash Jyoti Pathak. I am a PhD scholar in IIT Bombay, uh, and I'll be taking your doubt clearing session. I'm the TA for this course. Okay, so I'll now share my slides. Okay. Okay. So once again, good evening, everyone. I'm the course instructor of this course of the course NMR spectroscopy for chemists and biologists. I'm a PhD scholar in IIT Bombay, and your course instructor for this course is Professor Ashutosh Kumar, along with Professor Kusu. So I think I should now start with this week's doubt clearing session. So I'd like to uh, first solve. I'd like to see if we can solve one of the questions that was that is from week 8 and also a little bit from week 7 classes that you had. So the question is this: an RF pulse with a flip angle beta applied along the x-axis is represented by. So the options are beta x, e e to the power minus I beta x whole square, beta square, ix square. So I'll wait for a few moments so that you can think on this and try to answer what might be the correct option for this question. Okay, so I think now I should start explaining the answer to this question and what is the concept that you need to have to answer such questions. So the correct option is your option B. This is the correct option. E to the power minus I beta I x. So the concept that you should know to answer such type of questions is the concept of the product operator. So on the based on this product operator concept that is there in uh, quantum chemistry. If you have attended the lectures in the session of in week 7's classes and week 8's classes, then you might be able to answer this. So I'll just give a brief and revisit the concepts that have been discussed in that session. So yeah, this is based on the product operator. So why is it necessary? So product operator formalism, it is a mathematical framework, and it is as you might already know, that it is used to describe how nuclear spin operators evolve under the influence of radio frequency pulses and also under the influence of spin-spin interactions. So what is the use of this? Why go with this product operator? Because it simplifies the description of how the magnetization of spins changes during an experiment. So let's try to get a bit more into it. So this operator evolution under rotation. How does this operator evolve under this rotation condition? So the operator, what is the operator? The operator is this this operator e to the power I beta ix. It represents a rotation operator that, and it describes the evolution of spin states when the system undergoes a rotation by an angle beta about the ix axis. So the spin angular, the nuclear spin, that is happening in the x axis. Okay, so in that axis, the angle by an angle beta that the system rotates. So that is what is meant by this operator e to the power I beta ix. So in quantum mechanics terms, the rotation of a spin operator, like magnetization around a specific axis, is described by an exponential operator like e to the power minus I theta ix, where what is this theta? So theta, as you might already be knowing, so theta is the angle of rotation, right? Theta is what? Theta is the angle of rotation, and ix is the angular momentum operator. Okay, so spin angular momentum operator, in this case corresponding to the x component of the nuclear spin. So this formalism is widely used in NMR to describe how nuclear spins change when an RF pulse is applied. Okay. So on application of an external RF pulse, how it changes, how the nuclear spins that are there in my sample, they change. So that is denoted by this operator, which is uh, which is the which is equal to e to the power minus I beta ix. And so the expression, this e to the power I beta x, it describes how the magnetization evolves under a rotation around the x-axis by an angle beta. So this is a standard operation in NMR experiments when a pulse is applied. For example, we'll take an example here to understand it better. So for example, a 90-degree pulse is applied along the x-axis, and due to this 90-degree pulse applied, it will rotate the magnetization from, it is obvious that it will rotate the magnetization from z-axis to the xy plane, and specifically to the y-axis. Okay. So the operation is used to describe this. So if this is the situation that is happening, so the operator now will be equal to e to the power I theta. Theta is because a 90-degree pulse is applied. So e to the power minus I theta, in place of theta, I will put pi by 2, and it is the pulse is applied along the x-axis. So ix. Now, why are the other options wrong? So we should also understand that. So this beta ix, this is not the, this simply represents the x component of the angular momentum operator multiplied by a scalar beta. So this does not describe a rotation or evolution. So this is completely entirely wrong. Okay. Now, in case of C option, the C option was beta ix whole square. So this represents the square of the operator, right? It does not correspond to, sorry, uh, it does not, hmm, uh, Okay, so it does not, this represents the square of the operator and it does not correspond to a rotation or evolution in NMR. Right. And the D option, which is beta square IX square, this is a quadratic expression that also does not describe a spin rotation or time evolution. Okay, so this was your first question. So uh, I'd like to delve a bit deeper into this concept so that you understand it better. Just a moment. So just a quick revisit into the concepts that you have already learned in your week 7 and week 8 lecture classes. So, so you might have already learned about the uh, Liouville equation. It was already discussed. So we'll begin with that uh, Liouville equation with the Hamiltonian. That is, and that includes the radio frequency pulse explicitly. So that what is the equation? So equation with the Hamiltonian operator, it is equal to H equal to H naught plus H1 T, right? So what is this H naught? H naught. So H naught is the time independent part of the Hamiltonian, right? It is the time independent part of the Hamiltonian Hamiltonian, and time independent. H naught is the time independent part of the Hamiltonian, and H1 T. What is this H1 T? H1 T is the time dependent. It is the time dependent part of the Hamiltonian, right? Dependent part of the Hamiltonian of the Hamiltonian. So now, based on the Liouville equation, you will get this. If you do this, you will get equal to 5 H cross is equal to H by 2 pi, and that is equal to H naught plus H1 into T, right? So now, if your H1 were non-existent, then in that case, what would have been the solution? Existent. The solution would have been this solution would have changed to this. Okay, H naught T, right? And so we got H naught T. Okay, now we need to define and quantify another parameter, which is we define and quantify rho star. Okay, quantify this parameter such that what will be the case here? So that under such a condition, okay, it will be equal to okay. Now, what is it telling? So such a condition, such a solution, right? Such a solution satisfies the condition satisfies the condition that at t equal to 0, rho and this new parameter are identical, right? Okay, so now what we need to do, we'll differentiate the above equation with respect to time. Okay, differentiating with respect to time. Okay, this above equation, this one. So what we will get upon differentiation. What will be get. So slides there. Okay. So on differentiation, we will get what we will get is this, right? Equal to right. This is what we will be getting. So this will be equal to what? This will be equal to rho h naught plus h1. So from here, what will we get? From this, we get from this, we get this. We'll get this, right? H naught T and rho h1 e to the power minus I h cross h naught T, and that is equal to your I by h cross e to the power I by h cross h naught T, and this will be then equal to I by h cross h naught into T. So upon solving this, we will what you will get? We will get finally, we will get this, right? We'll finally get this. Where what is this h1 star? I will time. So this is equal to this e to the power I h cross h naught T into h h1 e to the power minus I h naught T. Okay. So now at t equal to 0, what will happen? At t equal to 0, at t equal to 0, h1 star is equal to this h1. So the transformation operator. So this is the transformation operator E I by h cross h naught T represents the rotation about the static field axis, and thus represents uh, okay, and thus represents the transformation into the rotating frame. So such a representation is also called the interaction representation. So this was already discussed in lecture 7. So like week 7's lecture. So under resonance condition, the evolution under H naught will be negligible. Thus, as we will during the high power short duration pulse, this Hamiltonian H1 star will be identical to H1, right? Similarly, rho star will also become identical to rho during the pulse. Okay. Now, if we solve, we calculate the matrix elements. If we calculate the matrix elements of H1 star. Calculate the matrix elements of H1 star So in that case, what we will get? We will get this, right? And will be equal to a e to the power I h plus h naught t e to the power I by h cross h naught t into h1 e to the power minus I by h cross h naught t. This is in the superscript. Okay. This so that will be equal to giving you this e to the power I by h e to the power I by h ek minus em t, and that is a h1 m a. So if h1 is equal to h1 at 0 e to the power minus I omega rf t, which is the RF pulse, which represents RF pulse. So then in that case, what will I get? I'll get this e to the power I by h is ek minus em minus h omega rf t. Okay, and this will be equal to k 0 m. Okay, so now this ek minus em minus h cross omega rf is in the kilohertz range, right? If t is in the microsecond range as in an RF pulse, then the time dependent term will be this. This is the time dependent term, right? This is this equation that I wrote. This is the time dependent term will be extremely slowly varying during the pulse, and hence can be effectively considered to be constant. Okay, thus the matrix element, this is the matrix element. Okay, this one. What will happen can be assumed, this can be assumed to be independent of time in that condition. Okay, independent of time. So in fact, under resonance condition, what happens? This term, this ek minus em minus h omega h cross omega rf will be 0, right? And there will be no time dependence at all. Okay, so in other what can we say? During the time of the pulse, what else can we say? We can say that during the time of the pulse h1 star can be assumed to be time independent and is equal to the amplitude of h1. Okay, so now if you if the RF pulse is applied along the x-axis, what will I get? This will be equal to, okay, so that is equal to gamma h cross h1 ix. So the transformation. So now this transformation, the transformation operator. So transformation operator, this is equal to e to the power. This is only this I h cross h Hamiltonian h1 t. This then becomes what? This is what becomes this e to the power minus I beta. Okay. is beta x. Okay. This beta, what is this beta? This beta is only your gamma h1 t. Okay. And it represents the rotation about the x-axis by angle beta. Okay. Flip angle of the, that is the beta, that is the pulse that I'm giving to the, to my, to my, the nuclear spins in the at equilibrium position to flip the nuclear spins by an angle beta. So thus, depending upon the length of the pulse, different rotation angles can be obtained. Okay. So, so this was the explanation for the first question. Okay. I think now you have understood the first question and the answer associated with it. Okay. So, so this was the question. The RF pulse with a flip angle beta applied along the x-axis is represented by. So now it becomes obvious, right? The correct option is this B, e to the power minus beta ix. Okay, the beta is the flip angle and ix is the pulse that is applied in the x direction. Okay, so now we'll move to the second question. Right. So what is the second question? The second question is, the second question says that for a spin with precisional frequency omega i, the field along z-axis in the rotating frame under resonance condition is. So the options are H naught. First option is H naught. Second is B. B is option B is 0. Option C is omega I by gamma. And option D is H1. So what do you think will be the correct option? I'll just give you 2 minutes to think on it. Okay, so we'll move ahead with the answer in this case. So the correct option is option B, that is 0. Okay, so why is it so? Why option B is correct? So this rotating frame of reference, this concept is something that you have already that has already been discussed in week 3 and week 4 classes as well. Okay, and this rotating frame of reference, why is it required? Because it simplifies the analysis of the spin behavior. It is used to simplify the analysis of spin behavior. So what does it do? This rotating frame moves at the same frequency as the applied radio frequency field. And this radio frequency field, which is typically tuned close to the Larmor frequency of the nuclear spins. Okay, so it moves at that same frequency. So this simplifies the complex motion of spins by reducing the effective precision frequency relative to the rotating frame. Right. So everything now becomes relative to my rotating frame. So in the laboratory frame, where the nuclear spins traces around the static magnetic field H naught at their Larmor frequency omega naught, where this Larmor frequency omega naught is equal to this gyromagnetic ratio gamma into this gamma dot H naught. So this is H naught. Earlier you might have in your in the class also somewhere, this H naught has also been represented as V naught also. Okay, but here because the options are with respect to H, so actually V naught is equal to H naught here. Huh. Instead of using the notation V naught, there here for the external magnetic field, the notation that has been used is H naught. So this gamma is what? Gamma is a gyromagnetic ratio, and H naught is the strength of the external magnetic field applied along the z-axis. Now, however, in the rotating frame, what happens? The precision of the spins is observed from a reference point that moves at the same frequency as the applied radio frequency field. Okay. Usually, this radio frequency field is close to the normal frequency of the spinning nuclei. Now, what is this resonance condition? The resonance condition in NMR occurs when the frequency of the RF field matches the precisional frequency of the nuclear spins, that is omega naught. Now, under such resonance, what happens? The following happens, right? This RF field drives transitions between the spin states of the nucleus, and in the rotating frame, the effective magnetic field along the z-axis therefore becomes zero, because the spin is now aligned with the RF field. Okay, so because of this change in the reference, now my external magnetic field effectively becomes zero, and all my net magnetization has shifted from the from the z-axis, positive z-axis, to the reference which I have selected, that is along the RF field. Now, find the other options from. So H naught, when this would be true, this would be true. H naught would have been true in the laboratory frame, right? So where the strong static magnetic field is applied along the z-axis. So however, in the rotating frame under resonance, this z field becomes zero. Okay, so this is wrong. The option C is what? Omega I by gamma. So this is related to the normal frequency in the laboratory frame, but in the rotating frame at resonance, this also goes to zero. Okay. In case of D option, the option D is this H1. This is the applied radio frequency field which exists in the rotating frame, but it is applied in the XY plane and not along the Z axis. Right? Because this is the RF field and it is applied along the XY plane, not in the Z axis. Okay. So this is also wrong. Right. So did we understand the concept? So let me go through it once again. So the question was, for a spin with precisional frequency omega I, the field along the Z axis in the rotating frame under resonance condition is okay. In the rotating frame. So the question it has been very clearly mentioned that the field along Z axis in the rotating frame. So when you have changed the frame of reference, okay, from the laboratory frame to the rotating frame, okay, and under such a condition, what is the field that that you will be seeing in the z-axis? Okay, so under such a condition, what happens? The field, you are changing the frame of reference from the laboratory frame to the rotating frame, and because of the change in frame, my the external magnetic field, that is this H naught, this becomes equal to this changes and becomes equal to this, the frequency changes to omega naught equal to gamma into H naught. Okay, so this was your second question. I hope it is clear. I will move to the next question. Okay, so next question is this. For a single spin I equal to half, the matrix representation or pi pulse along y-axis is given by. So as you might be knowing, these spins are represented in the form of matrix notation. So this option A is this 0 minus 1 minus I 0. The second matrix is 1 minus 1 minus I 1. Third option is 1 minus 1 1 1. And the fourth option is 0 minus 1 1 0. So I will allow some minutes for you to think and try to solve this question before explaining. Okay, then. So we'll try to solve this question. Okay. So uh, from the from we need to have a basic understanding of the fundamentals of quantum mechanics to answer and solve this question. This has been actually discussed in your in your week 7 and week 8 classes. So we'll just quickly revisit the concepts and understand why the correct option is option D. Okay. So why is this? So what does this actually represent? This D, this matrix notation is 0, minus 1, 1, 0. So it actually represents, if you have attended the classes, then it actually represents what? It represents a pi pulse. Presence a pi pulse along y-axis, right? Along y-axis for a spin half system, right? Spin I equal to half system. So this is for this system. This is actually the pulse. So yeah, this is what represents a pi pulse. I have system. Okay. So if we are considering the spin half system in quantum mechanics, then it can be represented as for a spin half system half system. In quantum mechanics, we can represent it as like as is the case as is the case that in case of NMR, we have two states. One is the lower spin state and another is the higher spin state. Okay, so the lower spin state is your alpha spin state, which is the spin state that aligns with the your external magnetic field. Okay, so that is your spin up state or alpha spin state, and it is your low energy spin state. So when we are representing it in terms of quantum mechanics, then your alpha spin can be represented as this alpha or the spin up state along. This is along z axis, along the positive z axis. Okay, and it is represented by the vector, represented by vector. This notation. This is 1 0. Okay, and for spin down state, down state, which is along the z axis. Hmm. along the negative z axis against the external magnetic field along this negative z axis. It is represented by z axis, but along the z axis, but the spins are opposite to uh, the z axis, positive z axis, nuclear spins are. Okay, so under such a condition, it is represented by this. Okay, so what does this states tell? So these states actually, it's these states form a two-dimensional vector space, right? This states represents a former two-dimensional vector space on this spin state, and operations on this spin states operations. This can be represented using the 2 cross 2 matrix, right? And operations on these spin states, spin states can be represented using 2 cross 2 matrices. Okay. Now, in quantum mechanics, okay. So now in quantum mechanics, quantum mechanics, the okay. Quantum mechanics, right? The rotation of a spin minus half of spin minus half particle along uh, about an axis. About an axis is described by the operator. Which operator? R theta. Particle is by the operator R theta, right? By the operator R theta. And what does it do? It which rotates this R theta. Okay, by operator R theta rotates the spin by an angle theta around the given axis. Spin by an angle theta around a given axis. Okay, so the general form of this notation r theta about an axis. So what is the notation? The general form of a rotation operator about an axis. It is given by this. This is the unit vector theta operator. So this is given by e to the power minus I theta I along the direction in which we are uh, considering. Okay. So what is this theta? Theta is the angle of rotation, right? This is the angle of rotation. And what is this? This is the spin angular momentum operator corresponding to rotation around the axis. And what is this? This is the spin angular momentum. Okay, momentum operator corresponding to corresponding to the rotation around the axis N. Around axis N. Okay. So this, and it can be an axis X, Y, or Z. Okay. So now for a Y pulse, say we consider a Y pulse. For a Y pulse, what will be the theta pulse? The theta in this case is Y pi. Sort of for a pi pulse, but theta is equal to, here the theta will be equal to pi about the y-axis. Say about the y-axis. Y-axis, the rotation operator will be an operator. This rotation operator, okay. This rotation operator becomes, what will be the rotation operator? Ry. The angle is phi. It will become e to the power minus I y. Right. So where this Iy is the angular momentum along the y-axis. So here the direction is what? Along the y-axis. So the angular momentum operator Iy is along the y-axis. Now let us consider the angular momentum operator for spin half system. Okay. So now for a spin spin half particle, right? Half particle, the angular momentum operators are represented by Pauli matrices, right? Momentum operators are represented by the Pauli matrices. Pauli matrices. Okay. So now, what is this Pauli notation matrix operator? What will be the case? So when represented by Pauli matrices, what will we get? The x component. The x component Ix is will be written as x component of the angle. X, that is Ix. Okay. Sorry for the interruption. My network had some technical issues. So I will be getting back again to where we stopped. Okay. 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 So we were looking into the Pauli matrix notation. So when we are considering the Pauli matrix notation, so in that case, the angular momentum, the x component of it is represented by this Ix equal to, this will be half. What are the possibilities? 0, 1 and 1, 0. Okay. And Similarly, the y component of the IY, that is represented by IY equal to 0 minus I and I 0. Okay. And the Z component or IZ, that is represented by IZ is equal to half 1 0 and 0 minus 1. Okay. So here we are interested in the y component because the pulse is applied along the y-axis. So as per the question, we are interested in this y component because the pulse is applied along the y-axis. Now the exponential of the Pauli matrices. So the rotation, so the rotation operator, okay, so the rotation operator for a pi pulse or a pi pulse about the y-axis is r. This will be written as ry pi is equal to what? E to the power minus I pi I y. Okay. Now to compute this we use the fact that the exponential of a Pauli matrix leads to a specific form, right? What is that specific form? To compute this, we will use the specific form of the Pauli matrix. Form of the Pauli matrix. Okay. So what is this? Yes, Pauli matrix. In this case, the specific form of the matrix, Pauli matrix, will be given as this R pi is equal to e to the power minus I pi y is equal to cos pi by 2 I minus I sin pi by 2 iy. Right? Iy. So where I is what? I is the identity matrix. Where this I is identity matrix. I is the identity matrix, and as you know, this cos pi by 2 is equal to 0 and sin pi by 2 is equal to 1. Okay, equal to 1 now. So the rotation operator therefore now will become, what will be the rotation operator now? Okay, so thus the rotation operator will become this R y pi is equal to minus I is equal to minus I half 0 minus I and I 0. right? So upon simplification of this equation, we get upon simplification, what do we get? We get y pi. This is equal to 0 minus 1 and 1 0. Okay. So what is this? What does this matrix define then? So this is the matrix that describes a 180-degree rotation. That is when a pi pulse is applied around the y-axis for a spin system that is having I equal to half for a spin half year system. Okay, what is this representing? This is the matrix that describes a 180-degree rotation, or this when this pi pulse is applied around pi pulse. Because of the pi pulse, this it describes a 180-degree rotation around the y-axis for a spin half system. So now this. So what does this do? The matrix, the matrix, the matrix that is 0, minus 1, and 1 0. What does it do? It represents the effect of a pi pulse around the y-axis. Effect of pi pulse around the y-axis. Along the y-axis. Pi pulse along, okay, along y-axis. Okay, along y-axis. So what does it do? This swaps the spin states alpha and beta. So it swaps. Okay, it swaps the alpha and beta spin states. So now what will happen? This alpha spin up. This alpha, this spin up. This is transformed into. This gets transformed into beta. Beta or the spin down state, right? Hmm. That will be therefore 0 and 1, 0 1. And this beta spin down, 0 1. This is transformed into, this is this is beta. That is this is transformed into alpha spin up, right? That is, this will become 1 0, right? So this is exactly what we expect from a 180-degree rotation around the y-axis. It flips the spin states, reversing the direction of the magnetization. Okay. Now we'll look at why were the other options incorrect. Okay. Why were the other options incorrect? So your option A was what? Your option A was instead. Option A was yeah, 0 minus 1 minus I 0. Okay. So your option A was this. 0, -1, and 1, 0. What does it represent? 0, -1, and minus I, 0. Okay. 0, -1, and minus I and 0. This was the your option 1. Okay. This introduces an incorrect phase factor. Right. This, what does this spell? This introduces an incorrect introduces an incorrect phase factor. Incorrect phase factor, and thus makes it an invalid representation, making it an valid representation, invalid representation of rotation along y-axis. Along y-axis. Now, what about option B? Your option B was, what was it? Let me check. Okay, option B was 1 - 1 minus I 1. Okay, why was it wrong? Why was it wrong? Option B was 1 - 1 and minus I 1. Okay, so why was it wrong? This matrix, this matrix does not correspond to any valid rotation for a spin of system. It has okay. This matrix does not correspond to any valid rotation for a spin half system. For a spin half system. Spin half system. It has incorrect phases. It has incorrect phases and does not swap the spin states as required by a pi pulse swap spin states as required by a pi pulse. Pulse. And what about option C? Option C was also incorrect, right? So what was wrong in case of option C? What was the options? What was the matrix? So 1 - 1, 1, 1. Okay. Okay. So 1 - 1, 1, 1. This was option C. So what does it? Why is it invalid? It is invalid. It is not a valid. It is not a valid unitary matrix, right? It is not a valid unitary matrix and cannot represent a rotation operation. Cannot represent a rotation operation. Rotation operation in quantum mechanics. Quantum mechanics. Mechanics. And it does not correctly swap the spin states. It also does not correctly swap the spin states. Swap the spin states. Okay. So this C option is also wrong. Right. So the only option that is correct is, yeah, D option. Okay. So this was a lengthy explanation for this question. So I think you have understood the question and the correct answer for this question was it option D. Okay. So I'll just Wait for 2 minutes so that you can absorb the knowledge. Okay, so I think you understood the explanation behind it. Okay. Okay. So now we'll move on to the next question. Okay. We have some couple of more slides to cover. So we will move on with the next topic. So one of the next topics that were discussed, okay, that was the basis operator, right? What is this basis operator? So this basis operator, it depends on the number of coupled spins, and it can be defined as Cartesian operators, single element operators, shift basis operators. So one spin will have four operators based on this concept. And for n spins, therefore, the number of elements in the basis operator will be equal to 4 to the power n. Okay. This is obvious. So if one spin has four operators, then for n spins, the number of elements in the basis operator that will be equal to 4 to the power n. Okay. So this is important. To the power n. Okay. So based on this concept, the one of the questions that we can solve is, let's see. Okay, so this is the question. So for a system of three spins, and each of the spin is spin half system that we are considering. So the total number of basis operator is your option A 9, or option B 27, option C 64, or is it option D 81? So what might be the correct explanation, the right answer? I'll just give 2 minutes for you to think on this answer. The correct option is option C. Okay. Why? Because because of the simple equation, the simple formula that we just learned in the earlier slide, last slide. That is this given by the number of basis operators is given by 4 to the power n. Okay. And then it represents the number of total number of spins that are there. So how many spin systems are there? There are three. Okay. So therefore 4 to the power 3. So we will get how much? 4 into 4. That is 4 to the 60, 16 for the 64. Okay. So that is the correct answer, option C. Okay. But we'll try to gain a bit of a theoretical understanding into it. Okay. So uh, what is this basis operator? So, as in the earlier yeah, slide, you saw that this basis operator can be defined in many ways. It can be defined in either Cartesian as Cartesian operator, or it can be based on single element by basis operator, or it is also known as what? Polarization operators. And also another way of defining it, the basis operator is on the basis of shift basis operators. Okay. So the number of basis operators will depend on the number of coupled spins, right? And as we had seen in our last slide, that for one spin it will have four operators, which form a complete basis set. So what are this? For one spin system, it will have four operators. So what are these four operators? Four basis operators. So in case of Cartesian space, okay. In case of Cartesian space, this Cartesian space. Okay, what are the four operators that you'll get? Four operators you'll get is this e by 2, right? Ix, Iy, and Iz, right? This was already there in your week 8 lectures. Okay, and now another way of representing this basis operator is single element operator space. So what are the four operators in this single element operator space? Operator space. What are they? They are I alpha, right? I beta, I plus, and I minus. Okay. And in case of shift operator space, what would they? Shift operator space. Shift operator space. They were, what would they? E by root 2, I plus, I minus, and I0. And this I0 is also I0. Right? This I0 is also given as root 2 IZ. Okay. So matrix, what will be the matrix representation of these various one-spin operators? What is the matrix representation? Do you remember? They were also explained. I'll just give a brief on the matrix representation of these operators, one-spin operators. Okay, so we'll quickly look into this. So the matrix representation of the operators. So we'll look into each of these operators. Okay, so Iz, this Iz is given by this half 1 0 0 minus 1, right? Ix is given by half 0 1 1 0. Okay, Iy is given as Iy half 0 1. Iy is given as half I 0 minus 1 and 1 0. Okay. Similarly, I plus is given as these were already explained and discussed. Okay. I think you have the key concept behind why I'm writing it like this. And I minus is represented as 0 0 and 1 0, right? Okay. And in case of I alpha, it is 1 0 and 0 0. And in I beta, it is 0 0 and 0 1. Okay. So now for n spins in a coupled network, there will be 4 to the power n elements in the basis operator sets. Now for example, so this is something you know, right? Something that we already did, that just discussed in the last two slides. So for n spins, okay, that are in a coupled network. For n spins in a coupled network, what is the case? In a coupled, there will be 4 to the power n elements in the basis operator sets. There are 4 to the power n, right? 4 to the power n elements in the basis operator sets. Basis operator sets. Okay. Like for example, if there are two spins, for example, for two spins, example again. We are considering example, for example, if there are two spins, okay, then how many total operators will be there? Then in that case, there will be 4 to the power 2. That is 4 into 4 equal to 16 operators will be there. Okay. Now for the Cartesian space, what will be, what are they? So for these Cartesian sets, for the Cartesian space, these are Cartesian space. These are, what are they? If we write, these are the 1x, then I1y, and I2x, right? Will go like this, I2x, I2y, I2z. Okay. Then next will be I2i, 1x, then I2x, then 2i, 1x, I2y, 2i, 1x, and I2z. Okay. Next will be what? 2i, 1y, I2x. Okay. 2i, 1y, I2y, 2iy, 2i, 1y, and I2z. And the last one will be 2i, 1z, I2x, then 2i, 1z, I2y, 2i, 1z, and I2z. Okay, so this will be it. Now, okay, so did you understand this? So next, for these three spins labeled as AMQ, the Cartesian operator sets would be 100. Okay, so now for three spins labeled as AMQ, the Cartesian operator sets will be operator sets would be again we will use that same concept for this also. This will be I, okay, I A P I M P I Q P for P equal to what? X, Y, and Z. Okay, that is a total of how many? A total of 9 operators. Of 9 operators. Okay. Again, there will be what? 2I A P I M R. Okay, M R. Then 2I M P I Q R. Then 2I A P and I Q R. Okay. So this P comma R is equal to XYZ. XYZ. The total of, in this case, there will be a total of 27 operators. Okay. How many operators? 27 operators. 27 operators. And for this 4I AP I MR and I QF QS, right? QS, that is for PR and S. There will be X, Y, and Z. Okay. So here also, how many? A total of 27 operators. Correct. Hmm. So similar products can be written for other types of basis sets as well. Ah, similar products can also be written for similar basis sets. But matrix representations for all these operators can be derived actually. Okay, you can derive these matrix representations. Not difficult, but it takes a bit of time. But if you are if you once try to solve the yeah, do it for once, then the concept becomes very easy. Huh. So conditions for now for one spin system, for one spin, what happens? The condition space representations are space representations are what is the condition? So, so in that case, it is equal to half 1001. Huh. Then Ix is what will be your Ix? Ix will be equal to half 01 and 10. Obviously, MIY will obviously be equal to half 0 minus I and I0. Okay. And Iz becomes equal to half 10 and 0 minus 1. Okay. So for for two spins, what will be the case? Now for two spins, for two spins, K and say for two spins, K and L. Okay. K and L. So it will be equal to E equal to half 10 and this will be K 1001 in the cross product and then 1001. Okay. So this is how you'll have to move ahead and you'll have to solve this. Okay. But you don't have to get into so much complicacy for this question at least. For this question, you just need to remember the formula that is for n number of spin systems, the total number of basis operator is given by 4 to the power n. Okay, but n is the number of spin systems. So for three spin systems, then will be equal to 3. Like in this question for three spin systems, it has asked. So 4 to the power 3, that is 4 into 4 into 4, that is equal to 64. So total number of basis operators will be therefore 64. Okay, this is the correct answer. I think this concept is also clear. Okay, so now moving on to next question. So the question is, in a three spin system, I equal to half the operator term IKX, IZ, IMZ represents. So the first option is Z magnetization of I spin, then Z magnetization of M spin, in phase X magnetization of K spin, X magnetization of the fourth option is what? X magnetization of K spin, antiphase to M and I spin. Okay. So which one will be the correct option here? So please take 2 minutes to think on this and try to answer it. Excuse me, I'll have some water by that time. Okay, so I think one minute. Okay, minute. I'm having some technical issues. Okay, so okay, actually, I was facing some technical issues. I don't know. My system started behaving randomly, suddenly. Okay, so we'll try to solve this question. So the question is, in the three-spin system, I have the operator term. So I think so the operator term IKX, IIZ, IMZ represents what? Okay, so the options are A, Z magnetization of I spin, Z magnetization of M spin, in phase X magnetization of K spin, or is it the D option, X magnetization of K spin antiphase to M and I spin? Okay, so the option is obviously the option is option D. Now, why is it this? The answer is X magnetization of K spin antiphase to M and I spin. So let's try to understand this. So the given operator. So as per the question, the operator, the given operator that is there, that is IKX, LZ, and IKX, ILZ, and IMZ. Okay. So what does this IKX represent? This IKX represents the X component of the K spin. Okay. So this is the X component of the K spin, and ILZ is accordingly this represents the Z component of the S spin, and IMZ it represents the Z component of the M spin. Now these are what? These are single spin operators actually. IKX, ILZ, and IMZ. These are single spin operators. So IKX alone, this IKX alone represents the X magnetization of the K spin. Okay. And ILZ and IMZ alone would represent the Z magnetization of the I spin and M spin respectively. So now when what has been done here? In this case, in this case, as you can see, these operators have been multiplied together. So IKX, ILZ, and IMZ, if they are multiplied, then they represent what? They represent the coupled or correlated states. Okay, they represent the coupled or correlated states. Now, now, in case of A, say option A, in case of option A, that is the Z magnetization. So it is solely represented by ILZ, right? It is represented by ILZ, involving not interaction with IMZ. Hmm. Now, in B magnetization of M spin, B Z magnetization of M spin. In case of B, the Z magnetization of M spin, this would be represented solely by, or this will be solely represented by IMZ, not involving IKX or ILZ. And in phase X magnetization of K spin, which is also known as what? In phase. In phase, this typically implies that the magnetization is correlated in a specific manner. Okay, so the magnetization is related in a specific manner. But here the operator includes ILZ and IMZ, indicating additional correlations beyond just the K spin's X magnetization. Right? Ready to understand this. So in phase, X magnetization of K spin in phase typically implies that the magnetization is correlated in a specific manner. But here the operator includes ILZ and IMZ. This indicates additional correlations beyond just the K spin's X magnetization. Okay. And now in case of option D was X magnetization of K spin antiphase to M, and L spin antiphase implies that the X magnetization of the K spin is opposite. or out of phase relative to the Z magnetizations of the N spin and I spin. Okay. So therefore, the operator IKX, ILZ, and IMZ, okay, this operator together, IKX, ILZ, IMZ, precisely captures this relationship, indicating that the K spin X magnetization is coupled in an antiphase manner with both the I spin and M spin Z magnetizations. Okay. So therefore, the correct option will be option D. Because this operator, this IKX, LZ, MZ, precisely captures this relationship. It indicates the case means X magnetization. It is coupled in an antiphase manner with both the L spin and M spin Z magnetizations. Okay. So the correct option is option D. Hmm. So did you understand? So why the correct answer here is option D. Okay. Ah. So next on, we'll move to the next question. Okay. One minute. Okay. So this is the question. Okay. So the question is 2ikx ILY plus 2ikay ILX represents what? What does this represent? Is it zero quantum coherence of spin k and L, double quantum coherence of spin k and L, mixture of quantum, double quantum and zero quantum coherences, or is it the D option, total k spin magnetization? So I will just give you a few minutes to think on this question and try to solve and answer, and then I'll give the explanation. Another 1 minute, then we'll start try to understand mm, this question, try to solve it. Okay, so I okay, so we will try to solve this question now. Okay, so uh, the question is that 2ikx iiy plus 2iky represents zero quantum coherence of spin k and spin k and L, double quantum coherence of spin k and L. Option C is mixture of double quantum and zero quantum coherences, and option D is total k spin magnetization. Okay, So the correct option is option B, right? That is the double quantum coherence of spin K and L. Okay. So what is this option? This this option is this double. The answer is the correct answer is double quantum coherence of spin K and L. Okay. Why? Because this has already been discussed. This double quantum coherence it refers to a state where the difference in magnetic quantum numbers between two spin levels is plus minus 2. Okay. So this difference is in the magnetic quantum numbers. Okay. The magnetic quantum numbers between two spin states, when it is plus 2 or minus 2, then it is known as double quantum coherence. Okay. So this type of coherence arises when two spins, that is these two spins, K, small k, capital K, and this L and L undergo simultaneous transitions that lead to a total change in their combined quantum numbers by 2 units. Okay. So the product operator formalism is used to describe the spin states and their interactions, right? So the terms involved in the given operator, what are they? As per the question, they are 2ikx, ily, and this plus 2iky, ily. Okay. So it represents interactions between the x and y components of the spin angular momentum of two different spins, k and l. Okay. So what does this represent interaction? What does this this information, this two ikx, ily plus 2iky, ily, what does it tell? It tells it represents the interaction between the x and y components of the spin angular momentums of two different spins k and l. Okay. Now this ikx, ily. What does this represent? This represent the this represents the coupling between the x component of spin k and y component of spin l. Okay. And this iky, ilx, this similarly represents the coupling between the y component of what? Of spin k and x component of spin l. Hmm. Now, as per the quantum transitions, the operator, this k, 2ikx, ily plus 2iky and ilx facilitates simultaneous transitions in both spins, resulting in a coherence that reflects a difference in quantum number by 2 units. Okay. What is that reflects a difference in quantum numbers by 2 units? In quantum mechanical terms, what does this mean? This means that the spin system can undergo transition where two spins are raised or lowered together, changing the total coherence ordered by 2. Total coherence ordered by 2. Okay. So now, what is the physical interpretation of it? So the physical interpretation is that double quantum coherence occurs occurs when both spins change their states in a synchronized manner. And this synchronization is precisely what the operator, this operator 2ikx, ily plus 2iky, ilx describes. Right. So what is the physical interpretation? Physical interpretation is that double quantum coherence, this occurs when both spins change their states in a synchronized manner. And this synchronization is precisely what the operator, so ikx, ily plus 2iky, ilx describes. So the simultaneous involvement of this ikx and ily and iky and ilx aligns with the physical behavior of the double quantum transitions. Okay, so this aligns with the physical behavior of the double quantum transitions. So then, why is it not zero quantum coherence? Zero quantum coherence, it involves transitions when the total magnetic quantum number remains the same. Okay, so the net quantum magnetic quantum number. Okay, that won't change. That will be the same. And that is because there is no net change in the spin states of the system. Okay. However, the operators here involve simultaneous changes in two spins. Okay. This involves what happens simultaneously. The two spin states are changing. Okay, one is changing to the other, and at the same time, the other is changing to the first one. So that is what is resulting in a net magnetic quantum number of zero quantum. That is what is known as zero quantum coherence, which requires a magnetic quantum number change to be zero. Okay, which requires a magnetic quantum number change to be zero. Did you understand? So, okay, so this is the concept. Hmm. I just give you a few moments to go through it once and try to understand it. Okay, in case you are having any any confusion, you can ask. So, what is this double quantum? So, the question in this question, the operator 2 ikx plus 2 iky Ah, what does it represent? So, it represents what? It represents the double quantum coherence of spin k and L. Why is it so? Because of this concept that double quantum coherence it refers to the state where the difference in quantum magnetic numbers between two spin levels is plus minus two. So either it will be plus two or it will be minus two. Okay. This type of coherence arises when two spins. This is they undergo simultaneous transitions and that lead to a total change in their combined quantum numbers by with the total change in that this case the double quantum coherence that will be by 2 units. Okay, and the product operator formalism, this is the product operator double quantum coherence. The product operator is used here is 2 ikx ILY plus 2 iky ILY. Hmm. Okay, this is because this IKX ILY, it represents the coupling between the X component of spin K and Y component of spin L. Okay, and this IKY it's similar. It represents what? It represents the coupling between the Y component of spin K and the X component of spin L. And in this case, the quantum transition that will be seen, it facilitates the simultaneous transition in both spins and that results in a coherence that reflects a difference in the quantum number by 2 units. So in quantum mechanical terms, this means that the spin systems can undergo a transition where two spins are raised or lowered together, changing the total coherence order by two. And this physical interpretation is that the two spins, both the spins happen in a synchronized manner in case of double quantum coherence. And this synchronization is precisely what this operator 2 ikx ILY and plus 2 iky ILX described. Okay, so the simultaneous involvement of ikx and ILY and iky and ILX aligns with the physical behavior of the double quantum transitions. Okay, so this is the concept. Okay, so now we'll move on to the next question. Next question is the following operators form a rotation group. Okay. IKX, IY, IKY, 2 IKX, IKX, 2 IKY, ILZ, 2 IKA, KZ, ILZ, I say C option C is IKX, 2 IKX, ILZ, 2 IKY, ILZ. The option D is IKY, ILZ, 2 IKY, ILZ. So, which is the correct option? Okay, so think I'll wait for a few moments for you to answer the question. I'll wait for 2 minutes more for you to uh, answer this question, and then we'll discuss this. This is the last question of today's session. I think if you have understood, if you'll be understanding all the concepts and the questions that I've discussed in this doubt clearing session, then it won't be a problem to answer the assignment questions of this week. You can expect more or less these type of questions in your assignment. And in case you are facing any difficulty in understanding any concept or understanding any questions in your assignment, you can reach me out via mail and write to me, and we can again take up those concepts for better understanding. Okay, the correct option is option B. Okay, why is this the correct option? You might understand. Okay, so the options were this IKX, IKY, 2IKX, ILZ. The option B was IKX, 2IKY, ILZ, 2IKZ, ILZ. So option C is IKX, 2IKX, ILZ, 2IKY, ILZ, and the option D is IKY, ILZ, 2IKY, ILZ. So the correct option is option B. Okay, so you will understand the concept here. Okay, so why is the correct option option B? So we'll try to. The option is which? The option is option B. IKX, 2I, KY, ILZ, 2I, KZ, and ILZ, LZ. Okay, so let's try to understand each of these terms first. Okay, so IKX, what is this IKX? IKX is an angular momentum operator, right? This is what is an angular momentum operator. Hmm. And what is this? 2KI, KY, ILZ. What is this? And there's these two terms, 2IK, ZILZ. Okay, are product terms. Okay, they are what? They are product terms. They are product terms. Okay, involving both. Involving what? Involving both the K spin and both the K spin and L spin. Okay, flowing both the K spin and L spin. So, and what? The terms, the terms 2I KY and this LZ and 2I KZ ILZ. These do not directly directly follow what the angular momentum commutation. Do not directly follow angular the angular momentum commutation. Momentum commutation. commutation relations. But these combinations can represent relations. But what happens? These combinations can represent symmetries. Combinations can represent, actually, these combinations can represent symmetries in certain systems. Okay, symmetries in certain systems. Okay, in systems, when which systems where where the where the spin, okay, where the spin operators are coupled. Are coupled. So these combinations can represent symmetries where the spin operators are coupled. So these operator terms can therefore generate what can they generate? Transformations. Okay, transformations that are similar to those of a rotation group in composite spin system, right? Group in composite spin systems. Okay, in composite spin system. So therefore, this can form a rotation group under certain conditions. Under certain conditions, therefore, this can form a rotation group under certain conditions. Okay. Um, okay. So now, in case of option C, what was wrong? In case of option C was what? I. What was the option C? 1 minute. Let's check it. Option C was IKX, 2IKX, ILZ, 2IKY, ILZ. Okay, write it down. IKX, what was it? 2IKX, ILZ, and 2IKY, ILZ. Okay, so this IKX is a valid angular momentum operator. This is what? Valid angular momentum, valid angular momentum operator. Momentum operator. Okay. And these terms, what are the terms? This 2I kx I lz and this 2I ky I lz. What does it do? They involve products of spin components, involve products of products of sorry products of hmm, involve products of spin components, which again complicates their what does it do? It complicates actually. It complicates their commutation relations. Commutation relations uh, with respect to simple angular momentum. Simple angular momentum. Okay. Momentum operators. Okay. And in case of the option D, what was option D? Option D was IK. What was it? 100. I'll check it once. Option D was 2IKY, 2I, yeah, IKY, ILZ, 2IKY, ILZ. Okay. What were the options? IKY, ILZ, 2IKY, ILZ. Okay, so this was the option. So what does this do? These are the two IKY, and so these are the angular momentum operators. These two are what? These two are angular momentum operators. Okay, angular momentum operators. Like in the above case, this IKX was the angular momentum operator. Okay, so this IKY and IL is the angular momentum operators. But the product, okay, but the product, that is to IKY ILZ, this does not transform. Okay, this thing, this does not transform. Okay, this does not transform. And therefore this set does not form a transition group. This set, this IKY ILZ and to IKY ILZ, this entire thing does not form a rotation group. No rotation group. Okay. So the correct option is what? The correct option is option B. Okay. IKX to IKY ILZ and to IKZ ILZ. Okay. This is because the operators in this set can generate transformations that form a rotation group in composite spin systems where spin operators are coupled. The combinations of angular momentum operators and spin products in this option can still obey the general commutation rules of a rotation group despite involving spin coupling terms like 2IKY, ILZ and 2IKZ, ILZ. Okay, so this is the reason why the correct option is option B. Okay, so this was the last question. You have finished discussing the questions of this week's. Okay, the expected questions that you might get and the doubt clearing session for this week. Okay, so we will again meet in the next week. Okay, so goodbye for now.